Welcome to The Explainer. Today, we're going to pull back the curtain on the internet. We're going to follow just one single click from your mouse on this absolutely incredible journey, to the other side of the world and back, all in literally the blink of an eye. I mean, it feels instant, doesn't it? But in that tiny fraction of a second, there's this amazing high-speed relay race happening completely behind the scenes. So come on, let's follow that click and see exactly where it goes. So, before your request to see a web page can even start its journey, it has to be prepped for travel. It can't just go out on the digital highway as a blob of raw data. It needs to be packaged up very carefully. And the best way to think about this as like one of those Russian nesting dolls. This process is called encapsulation, and it's aided by a theoretical blueprint called the OSI model. Just think of it as the perfect 7-layer instruction manual for how to pack data. Okay, so it all starts at the top, in what we call the application layers. This is where your request is actually created and formatted. Then the transport layer jumps in. It chops your request into smaller chunks called segments and slaps a port number on each one. That port number is crucial. It's like a specific apartment number that makes sure the data gets to the right application on the server, your web browser, and not your email client. Let's go down to the next layer and see how this doll gets bigger. The network layer takes that segment and puts it inside a digital envelope we call a packet. And this is where the main address gets added, the IP address of the destination server. So if the port number was the apartment number, the IP address is the street address for the entire building. We're almost ready to send this thing. The data link layer adds the final wrapper, turning our packet into something called a frame. Now this adds two really important things: a header with the physical MAC address for the very next stop on the journey, and a trailer at the very end. That trailer is like a quality control stamp. It's used to check if the data arrived perfectly without any errors along the way. And finally, the journey actually begins. At the physical layer, that fully packaged frame gets converted from digital ones and zeros into actual physical signals that can travel across the network. We're talking electrical pulses for a copper cable, little flashes of light for fiber optics, or radio waves for your Wi-Fi. So here's a really key point. While that 7-layer OSI model is the perfect textbook explanation of how this all should work, the real-world internet actually uses a more practical, streamlined 4-layer version called TCP/IP. It kind of squishes a few steps together for efficiency, but that core idea of wrapping the data layer by layer, that's exactly the same. All right, so now that we've seen how the message gets all bundled up, let's zoom in on those two critical addresses that make sure it doesn't get lost in the mail. The best way to think about it is this. The IP address is like the main address on a letter. It gets the packet to the right city and the right street, the correct network. But once it's arrived on that local street, the MAC address acts like the specific mailbox number, making sure the packet goes from the local router to your exact computer and not your neighbor's. One address gets it across the globe, the other gets it the last few feet. Okay, so our data is packaged, it's addressed, it's been turned into a signal. So what kind of roads can it actually travel on to get where it's going? For most of us, that journey starts on a copper road. The good old Ethernet cable. The different categories, or CATs, are basically different speed limits. A standard Cat5e cable, the kind you probably have at home, is perfect for gigabit speeds. That's great for streaming, gaming, all that stuff. But a huge data center, they need the superhighway of Cat6a to handle a massive 10 gigabits of traffic without breaking a sweat. But for the absolute fastest highway, the Autobahn of the internet, we use fiber optics, which sends data as literal pulses of light. Single-mode fiber is the long-distance marathon runner. It uses a powerful laser to shoot signals for dozens, even hundreds of kilometers, connecting entire cities. Multimode is more like a sprinter, perfect for blazing fast connections over shorter distances, like inside one big data center. But what about when you can't run a wire? Well, for a long time, satellite internet meant connecting to a single geostationary satellite, way out in a high orbit. The problem with that? The sheer distance created this massive delay, or latency, of over half a second. That's that really annoying lag you sometimes feel on a video call where you're talking over each other. And this is just a brilliant example of how fast technology moves. Modern systems use thousands of low Earth orbit, or LEO, satellites that are much closer to us,
And just by closing that distance, they have slashed that delay from over 500 milliseconds down to around 40. That's a game changer, making satellite a real competitor to internet on the ground.
Okay, so our signal has crossed oceans, it's crossed continents, all at nearly the speed of light. It has arrived at the destination server, so now what happens? Well, that whole Russian nesting doll process, it has to happen completely in reverse. Yep, this is called de-encapsulation. The server first checks that frame's trailer to make sure no data got messed up in transit. Then it just strips off the headers, one by one. Off comes the data link header, then the network header, then the transport header, opening each layer of the package until it's left with the clean original data of your request. Only then can it hand it off to the web server application. So the request arrived, safe and sound. But wait a minute, let's think back to the very beginning. How did your computer even know the IP address to send the request to in the first place? And for that matter, how did your computer get its own address? This is where a few of the internet's unseen helpers come into play. First up is DNS. When you type google.com into your browser, your computer has no idea what that means. It first has to ask a DNS server to look up that name and translate it into the numerical IP address the network understands. Without DNS, we'd have to memorize long strings of numbers for every single site we wanted to visit. It is truly the internet's phone book. And how does your computer get its own IP address? Well, that's handled by a service called DHCP through this really simple 4-step handshake called DORA. It stands for Discover, Offer, Request, and Acknowledge. Your device basically shouts out, "Hey, I need an address." That's Discover. A server replies, "How about this one?" That's Offer. Your device says, "I'll take it." That's Request. And the server confirms, "It's all yours." That's Acknowledge. And it all happens automatically in seconds. When you step back and look at the whole thing, this incredibly complex dance works for one simple reason: global standards. These agreed-upon rules are what allow billions of different devices, made by thousands of different manufacturers, to all speak the same fundamental language. It's the invisible agreement that makes the internet a truly universal network. Now, this system has served us incredibly well for decades, but the world of networking is always changing. And right now, the biggest shift we're seeing is the move away from specialized hardware boxes and into the flexible world of software. See, it used to be pretty simple. If you needed a router, you bought a physical router box. If you needed a firewall, you bought a firewall box. Today, that's all changing. Thanks to a concept called network functions virtualization, all of those single-purpose boxes can just be replaced by software. Think of them like apps running on a powerful, standard server. This makes networks unbelievably flexible and so much faster to build and to change. And this leaves us with a really fascinating question to think about for the future. As our critical network infrastructure literally turns into lines of code, where does the physical world even end and the virtual world begin? The journey of your data isn't just about signals on a wire anymore. It's a journey through layers and layers of pure logic. And now, every time you click, you'll know just how deep that rabbit hole really goes.